In today's lesson, we're going to look at scientific notation. Scientific notation is used often in science courses like physics or chemistry because it's used to express very large or very small numbers. And the other important thing to know is that the computations use the rule of exponents, which is why it's in this unit of the math. So if you think of all of the rules of exponents that you've learned, you'll be using the more basic ones when we do computations with scientific notation. The form for a number in scientific notation looks like this: a times 10 to the power of n, where the absolute value of a is greater than or equal to 1, but less than 10. So this number in front of the exponent, or times 10 to whatever power, has to be between 1 and 10. It can be equal to 1, but not 10. It must be less than 10. And it can be positive or negative, okay? And n, the exponent on the 10, is an integer. So let's look at some of the powers of 10. 10 cubed is, recall, 10 times 10 times 10, so it's 1,000. And a little trick that a lot of students use to remember these is that you just have the number of zeros on the 1. The exponent gives you the number of zeros. So 10 to the power of 8 will be a 1 with 8 zeros behind it. 1, 2, 3, 4, 5, 6, 7, 8. 8 zeros. Okay, but what about the negative exponents? If you go back to our exponent rules, when we have a negative exponent, that's the same as saying it's 1 over 10 to the positive exponent. So that's 1 over 10 squared, which is 1/100th. So now you can see that a negative exponent is going to be used for this very small number piece in scientific notation. And 1/100th is 0.01. So we've got a smaller number, we've got a number less than 1, and we can look at the decimal places or the number of spaces that we've moved the decimal place. So a -2 means that decimal place has moved 2 spaces from the one it's moved left 2 spaces. 10 to the -7 will be 1 over 10 to the power of 7, so a 1 with 7 zeros. I'll just put the commas in there, so it's 1 over 10 million. So that'll be 0. Okay, so the zeros between the decimal place and the 1 are actually 1 less than that. So this is 1 over 1/10 million. So you think tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths place, or you think about moving that decimal place 7 spaces. So when we just say a 1, the decimal place is after the 1. So we're moving at 1, 2, 3, 4, 5, 6, 7 spaces to the left to get 10 to the -7. Okay, so as a little reminder here, we can say that positive exponents give us large numbers, and negative exponents give us smaller numbers. Okay, in fact, numbers that are less than 1. Okay, and that's just the negative on the exponent. The negative, if it's a negative number in scientific notation, the negative will be out front, and you'll see that in the next example. So here we've got 3 numbers that are in scientific notation, and we'll convert them to decimal notation. Okay, so I've got 3.4 times 10 to the power of 4. Now you could think of this as 3.4 times 10,000. So that'll become, well, 10,000 times 3 is 30,000, and that'll be another 4,000. So you could think of that as 34,000. Instead, write the digits, and since that's a positive exponent, we know it's going to be a larger number. think of how many decimal places you need to move over, because every time you move a decimal one space, you've multiplied by 10. So we've multiplied by 10, by 100, by 1,000. We need to move it 4 decimal places. So there's our answer, 34,000. Okay, so the 34,000 is the answer to this one. So let's take a look at B. I've got negative 4.6 times 10 to the power of 2. And I could think of that 10 squared as 100 and multiply 4.6 by 100. But instead, just write out the digits and think about 100 means I'm moving it 2 decimal places. And I'm making the number larger, so move it 2 decimal places and put in zeros. So I've got negative 460. Okay? So 2.17 times 10 to the negative 4, oh, there's one of those negative exponents. It's going to be a number that's smaller. And I'm going to move the decimal place left 4 spaces, which really shows I'm dividing by 10 4 times. So I write down my 217, stick a bunch of zeros in front, and so my decimal was after the 2, so now I'm going over 1, 2, 3, 4 spaces. There's where my new decimal is, 0.00217. Okay, so really you can think of it as the exponent on the 10 tells you how many spaces to move, a positive, how many spaces to move the decimal place. A positive exponent means you're moving the decimal place to the right to make a larger number. A negative exponent means you're moving it to the left to make a smaller number. Okay, so here we have a few numbers. Let's practice changing them to scientific notation. And many students find this part easier than the first part. So I've got 21,670,000 here. So I'm going to always put the decimal place after the first digit, 2167. Let me just fix that up. So I've got 2.167. Oh, now my marker has changed. So this is what I'm going to have, and it's going to be times 10 to the some power. So think, how many decimal places do I need to move this to get the decimal from here at the end of the number to after the 2? And I'm moving it 1, 2, 3, 4, 5, 6, 7. So that's 2.167 times 10 to the power of 7. In step question E here, I have a very small number, but the same rule applies. It'll become 5.61. Put the decimal after the first digit. That way you're getting a number between 1 and 10. And it'll be times 10 to some power, and think, how many spaces did I have to move the decimal place? I moved it 1, 2, 3, 4, 5. So it's negative 5. And since this is a negative number, I stick a negative in front. A couple of years ago when I wrote this lesson, I went onto a population clock on Google, and this was the current population of Canada, rounded off, 34,600,000 people. So let's express that in scientific notation. So again, here's a really good time for you to press pause, do these 2 questions, E and F, and then press play and see if you've done them correctly. So I've got so I'm going to do 3.46, and again times 10 to some power, and just count how many spaces you've moved the decimal place over. So 1, 2, 3, 4, 5, 6, 7. And then Canada's national debt. And Canada's national debt means how much the government owes. So how much the government has borrowed to do over the years to do things like build airports and so forth. So it's, let's see, here's the thousands, the millions. So these are the billions. So 569 billion, $100 million is what the government owes. This does not consumer debt, which is what people owe, rather national debt. So that'll be 5.691 times 10 to the power of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you can see that those high exponents on the 10 really mean very large numbers. Before we do any computations, it's good to recognize when a number looks sort of like it's in scientific notation, but isn't quite. So here are a couple of examples. They all look sort of like scientific notation because they're 10 times 10 to the some power. But if you look closely at the first part of these numbers, that first factor is not in proper form because it's not a number between 1 and 10. So there's a couple of ways to go about doing this, and I'll explain both ways for these examples. One way would be just the first method is just look at that number and turn it into scientific notation. So that 0.327 should be 3.27. And because I've had to make the number larger, because this number is less than 1, it's actually times 10 to the negative 1. So that's just the 0.327 piece. But the whole thing is times 10 to the power of 4. So now I can use my exponent rules and say that's 3.27 times 10 to the power of, because I'm multiplying these two 10s that with both have the same base, I can add the exponents. So negative 1 plus 4 gives me 3. So this number is 3.27 times 10 to the power of 3. So that's the way to really think about the meaning of your scientific notation. The second method that I would use, and again, look at the first part of this number. There's actually two factors. These two things multiply to give me the same number. So I know that the left one I have to change to 3.27. So I've multiplied it by 10. So to keep the total value the same, I'm going to divide the second part by 10, which means reducing its exponent. So then I've got 10 to the power of 3. So that's another way of, this is a second method of coming up with the correct scientific notation form. So again, let's take a look at H, or try, again, press pause, try these, and then check your answers. So if I look at H, I've got 212 times 10 to the power of 7. Well, 212 is 2.12 times 10 squared because I've moved the decimal place over twice. So now that's times 10 to the power of 7. I'm multiplying here, so I add my exponents, so I get that this is equal to 2.12 times 10 to the power of 9. The other way to look at it, using our second method, is to say, well, that 212 needs to be changed to 2.12. I've divided by 10 to the power of 2 because I've moved the decimal place over twice. So I've made this smaller, this factor smaller by 10 to the power of 2. So I have to make the other factor larger by 10 to the power of 2 by adding a 2 to the exponent in order to keep the total value the same. And likewise, let's practice this one where I've got 56.4 times 10 to the negative 7. Remember your rules in working with integers. So that 56.4 is going to be 5.64 times 10 to the 1 because I've made this number smaller by a power of 10. And times 10 to the negative 7. So I'm adding the exponent. So I have a 1 plus a negative 7. So that's 5.64 times 10 to the negative 6. And again, using our second method, 56.4, I need to make it smaller by 1 power of 10. So that means I have to raise the exponent on the second part by 1, so it goes up to negative 6. Use whichever of these methods makes the most sense to you and that you can consistently use correctly. It doesn't matter which one of them you use. All right, multiplying and dividing. We need to use our exponent rules for this. And these numbers, sometimes these numbers are going to be too large to fit in your calculator, so it does not make sense to change them to decimal notation. Keep them in scientific notation. If you think about this multiplication, this is 7.1 times 10 to the power of 5 times 5 times 10 to the negative 7. Because it's all multiplication between these, I can actually change the order. So it's really could be thought of as 7.1 times 5 times 10 to the power of 5 times 10 to the power of negative 7. Well, 7.1 times 5, I can pull out my calculator and get 35.5 for that. And I can use my exponent rules here. 5 plus negative 7 is negative 2, so it's times 10 to the negative 2. And with a very quick calculator step, I've solved that without having to convert those numbers to decimal notation. And that's our goal. If I wanted to calculate Canada's debt per person, I want debt per person. So I'm going to take the Canadian debt and divide that by the population so that I know how much each person in Canada owes as far as the federal debt goes. So that's a dividing question. So that would be 5.691 times 10 to the power of 11. These are the numbers from earlier in the class, divided by 3.46 times 10 to the power of 7. Now, if you look at just the right side here, I've got the same bases with these tens, so I can subtract those exponents. So my answer is going to be something times 10 to the power of 4. And we can just pull out our calculators and divide those two numbers. So 5.691 divided by 3.46, and I get, and I'm going to round that off, 1.64 times 10 to the power of 4. Now, in case you're curious, it might be useful to turn that into decimal notation so that you know exactly what portion of the federal debt you owe. So that's times 10 to the power of 4. So I'm going to move the decimal place 4 spaces. So that'll be 164 and 2 more zeros. So you owe $16,000, $16,400 to some bank somewhere per person. Okay? A neat exercise would be to go onto the population clock, and you can find debt clocks as well, and compare Canada's debt per person in 2015 to, for instance, America's debt per person, and see which country owes more money. And you may find that kind of interesting.